at Rapid 2023, 3D printing is more than just about making parts from raw material. It's about a holistic approach to the process. I'm with Chris Schuppe. He's General Manager of Technology and Engineering at GE Additives. Chris, we've come from a world where when we make production parts, we design, prototype, iterate, a long, complex, slow process, basically. And one of the things about 3D printing was it offered the ability to make an infinite number of physical prototypes and iterate our way to success, but with a similar basic overall approach. But can we use something more advanced than that, something more simulation-based to cut that development time?
Absolutely. One of the things we've been working on with our new binder jet technology is the ability to simulate the entire process from really the CAD model generation all the way through sintering, and even post-sintering that can inspection-based compensate that model back to make a conforming part within 2 prints. And that's something we've really tried to develop as, like you said, you can iterate hundreds of times, but that really impedes the progress of a production part. This allows us to get to production more quickly.
Well, it's funny you mention that, because one thing we know, of course, is that working with any, whether metal or polymer parts, basically, is that nothing really ever is the dimension that you think it is in the way it's designed. Things shrink. There's depending on sections, you may have to tweak a wall thickness to compensate for thermal effects or cooling effects at the same time. Can those things be addressed now at the design phase, do you think, before we actually cut metal or make parts?
We're getting a lot better at it. I would say 5 years ago, absolutely not. Today, I would say for probably medium-sized parts, we get pretty darn close with the first iteration. For very large parts, and you'll see some of the large parts in the booth here, maybe it takes us 2 iterations where we do a pre-simulation, we print, then we measure that part, and we go back and we inspection compensate that part. And really, we're not playing with just CAD geometry, we're playing with the physics of the actual binder burnout and the entire sintering process through that simulation.
Well, it's a good thing you mentioned that, because of course the idea here is to actually mass produce cost-effective parts, and that's a lot more than just actually sintering something. We tend to think of the primary production process, not secondary operations, those other things. Do you have to simulate the entire process from beginning to end, or how do you break up the simulation task?
So we start with the CAD model, and then we're basically taking that CAD model, simulating the printing process, and then simulating the curing and sinter portion of that process. And then what we do is we actually distort the initial CAD model to what we call a pre-compensated shape that we know when we print it and sinter it, it will turn out to the exact geometry that the customer is looking for. So really trying to create an entire digital thread from start to finish of that process so that the customer doesn't have to think about that in great detail. They're just utilizing simulation to basically prevent printing a whole bunch of times.
Well, one of the interesting things about additive, of course, is your lot size can be 1, or your lot size could be 10,000. Right. In your case, you're quite famous for making, of course, the famous jet engine, fuel nozzle, right. Highly complex part, something which presumably will be made in the thousands. By the same token, you might do, for example, a surgically implantable material, a custom hip implant in which the lot size is 1. So is that development simulation process the same for a single part, say 10,000 parts?
Yeah, so we also have the same process for our laser process as well. So we can simulate a single part, we can simulate making hundreds of parts. In the case of binder jet, we can print actually, 1 part and 100 of those in the same build, or we could print 100 different parts in the same build. So depending on which one you build, it may change the simulation. So you're going to go through that simulation, and you don't want to print 100 different parts of one and come out with 100 bad parts. So trying to use that simulation capability to really accelerate development and increase and take advantage of the capability of additive to be super flexible manufacturing.
In large engineering firms, of course, it's possible to assign a single individual who's an advocate for a process or is an expert that way. Small to medium-sized firms, not so much. Is it necessary to have a single individual immerse themselves fully in the specific technology to make this work, or can you take general engineering design principles and make it work with this additive process?
I think with binder jet, the good news is a lot of the sort of support structure and rules that exist in laser kind of go away with binder jet because it's really a self-supporting technology. Where it gets interesting is when you get to really thin members or thin walls. In the green state, the part's relatively fragile compared to, say, a cast part or a fully melted part. So part of the simulation is understanding, will that part survive the sinter process? And so there's a little bit of knowledge that needs to come there, but I would say it's probably the simulation can bridge the gap from basic engineering knowledge to a good printed part.
And if injection molding professionals, of course, are well familiar with problems of support and shrinkage, thin wall, this parts, of course. Individuals that make historically machined or stamped parts, a different set of problems that way. In your opinion, would an individual coming from a machining or metalworking background or a polymer injection molding background, would one have an advantage over another in transitioning to this technology?
I think it's closer to probably injection molding or casting, in the sense of, casting has shrink, casting has design rules, runners, insulation, all those kinds of things that exist in a casting. There's similar types of rules, different rules, but similar types of rules for binder jet that can help, the expertise, having the expertise can help get to a better part faster. We're trying to build a lot of that expertise into the software so that it doesn't take, generations to develop that capability. You're developing that capability very quickly. Binder jet is itself also, if you think about the lead time of castings, tooling lead times are, anywhere from weeks to months to years in some cases. Binder jet doesn't really need that tooling, so the ability to go fast, and even if you have to iterate through that simulation a few times, you can do it in days, not weeks or months or years. So we look at it as a game changer for that type of industry, for competing against castings, and really looking for the opportunity to kind of disrupt traditional methods of manufacturing.
One prototype or no prototypes at all, is that the future of this technology, do you think?
I would say today it's one prototype, but certainly the goal is to get to no prototypes and you can get production parts straight out of the machine. Depending on the complexity of the part, we probably can get there in no iterations today, but most parts we would say at least one iteration.
At Rapid TCT 2023, the air was electric. The excitement about manufacturing America is palpable. New technologies, new ways of implementing additive manufacturing, not just for prototyping, but as a true production process, were all over this show floor. The future looks very bright for manufacturing America based on what we have seen here. Thanks for joining us on the show floor. See you next time. Today's episode is brought to you by Engineering.com, a globally trusted source for engineering content. Check out this and many other exclusive videos for the engineering professional found only on Engineering.com TV today.